with the Center for Safety Critical Structure Systems at IIT Madras. Today we have Professor J.M. Kishen from the Department of Civil Engineering, Indian Institute of Science, Bangalore, who is going to talk about mechanisms of crack growth in quasi-brittle materials, microcracking to fracture. As many of you know, fracture mechanics is not only constrained to the materials and the the aircraft or the metallurgy group. There is also a lot of interest from the other groups of the engineering. So civil engineering constitutes a major chunk of it. Of course, petroleum engineering, piping industry, so many are there. So today we are going to focus on the civil engineering aspects of the quasi-brittle materials. So Professor Chandra Kishen does not require an introduction to many of you, but nevertheless, for the sake of completeness, I'm going to do that. So I'll be probably brief, and Professor Chandra Kishen to excuse me for this brief introduction. He's a professor at the Department of Civil Engineering. He has completed his PhD at the University of Colorado, Boulder, USA, and he has held visiting faculty positions at Leipzig University of Applied Sciences in Germany, as well as at University of Colorado and the Russian Academy of Sciences in Kazan, Russia. He has been bestowed with the Best Teacher Award at the University of Colorado, and his research interest, of course, there are some awards from the Indian side as well as from the Karnataka government. His research interests are in fracture and fatigue with applications to residual life assessment and health monitoring of damaged structures. So he's got 167 research papers in the international journals and conference proceedings to his credit. He's an active consultant and has helped the industry solve challenging problems involving rehabilitations of metro girders, damage due to construction faults, large IT structures, damage due to fire accidents, highway viaducts, damage due to loss of pre-stress, and others. Wow, very interesting topic. So he is nominated as the Fellow of the International Association of Fracture Mechanics of Concrete and Concrete Structures and currently serves as its president. He is also the recipient of the Professor Satish Dhawan Young Engineer State Award by the Government of Karnataka. With these few words, now I will request Professor Chandra Kishen to deliver his lecture. All participants will mute their mics, and if they have any questions, the question and answer will be at the end of this presentation. So you can type it in the chat box. We will take it up one after another. Thank you.
Yeah, thank you, Professor Gopakash, for this introduction and also for inviting me to give this talk. And good evening to all of you. So I'll be the next 1 hour. I'll be talking on the mechanisms of crack growth in quasi-brittle materials, especially concrete, okay, from micro cracking to final failure. Yeah, before I start my work, I would like to acknowledge the people from whom I have learned a lot. All my students. These are my students. Okay, Dr. Sonali Sare, Parviz Fatima, Sudakshina, Kirtana, Parvinder, Nitin, and Yogesh. In fact, I think our learning, it takes place from our students because they are very young, active, energetic, and lot of enthusiasm in them. So, yeah, going to the outline of my presentation. Let's see if I have a cursor. Can you help me? Where do I find the cursor, the pointer here?
You need to right click on the mouse and you'll get the options of pointers.
Yeah, I'm not getting that's what I thought. Let me just check once again.
You're using PowerPoint.
Cursor, yes,
Okay.
yes.
Yeah, then
Yeah, it
you
is
right
moving.
click on your.
Do you see the cursor?
Yes, yes.
Cursor on the screen?
Yeah, on the introduction, it is
Okay,
right
fine.
now.
Then I'll use the cursor. That's fine. Yes. Yeah. So the outline of this presentation would be, I'll just switch off. Starting with a brief introduction, I will state the open research problems in the area of quasi-brittle materials, and talk about how the micro cracks transform into macro cracks and the experimental results of the experiments which we have performed using acoustic emission and digital imaging, and then some analytical formulation using the laws of thermodynamics, and I'll end with some concluding remarks and future directions. Okay. There's yeah. So let me first introduce this quasi-brittle material, which is concrete in the present case. So concrete, as you all know, is widely used in all the construction of infrastructures. So this is a highly heterogeneous material. Basically, heterogeneity comes from the different sized ingredients which go into its preparation. We have the large sized coarse aggregates, we have the fine aggregates, then we have the cement and water. So this makes the material very heterogeneous, and it is known as a quasi-brittle material. Basically, when we look at the load deformation response under tension, we see that we have an initial elastic region, okay, linear elastic region as shown in this curve, and then after it reaches the peak, we see a very nice softening response as shown by this curve here. So that is why it is termed as quasi-brittle. And the reason why it behaves in this manner is because of the presence of a complex zone known as the fracture process zone, which is present ahead of the crack. This is analogous to the plastic zone in ductile materials. But the difference is here we have a zone containing a lot of micro cracks, and these micro cracks are around the aggregate. You can see like you have an aggregate here and you have mortar surrounding it. So there is a interfacial transition zone wherein a lot of micro cracks are present at this junction. And also, as the crack, there's a lot of micro cracks in the mortar in front of the crack, in front of a true crack. These aggregates, the large aggregates, will provide resistance to the crack propagation, and the crack has to go around the aggregate, or sometimes it passes through the aggregate. So crack branching takes place. So the crack path is not a smooth path. It is a very tortuous path, okay, containing this bridging of aggregates and so on. So a lot of toughening mechanisms occur in this fracture process zone. Okay, and one of the most important aspect of concrete is it shows a size effect. Meaning, if you look at this figure here, so on the vertical axis we have the nominal strength, and on the horizontal axis we have the characteristic size, or some kind of a representation of the size of the structure. So here we have a horizontal line here depicting the strength criteria or the yield criteria, and we have this slope line, I mean which is the linear elastic fracture mechanics behavior. So when this concrete structures, when you have small size of the concrete structure, it follows the strength criteria, but large structures follow the linear elastic fracture mechanics. This is because in large structures, the size of the process zone is very small when compared to the actual crack size. So it follows the linear elastic fracture mechanics. But when I say large structures, it is as large as dams, like, where you have like the size of the structure is very massive. And when we compare to like its constituents, like the aggregate size and so on, whereas most of the laboratory testing and most of the structures fall in some intermediate group here. intermediate size, wherein neither linear elastic fracture mechanics principles are applicable nor the strength criteria. So here the size of the process zone is really large, comparable to the crack size or comparable to the size of the ingredients here. So this because of the presence of the fracture process zone, we cannot apply the principles of linear elastic fracture mechanics. So some principles of nonlinear fracture mechanics have to be applied. So that constitutes the quasi-brittle material. When we come to concrete structures, as I told you, the concrete is heterogeneous, quasi-brittle. There are a lot of micro cracking takes place in the fracture process zone. A lot of toughening mechanisms occur. But and also, when you look at the size, the loads which act on this structure, very seldom we have a concrete structure wherein we have simply a monotonic or a static load. We have most of the time, like concrete structures are subjected to fluctuating loads known as fatigue loads, which are random in nature, and this fatigue leads to progressive, localized, and permanent damage in the material. So because of this permanent damage, we can, it's a very good material for applying the principles of thermodynamics, especially the principles of irreversible thermodynamics to explain the process of damage in the material. See, from the literature, as we all know that fatigue, especially when it comes to ductile materials, fatigue is very well explored. There are a lot of laws which people use starting from the SN curves. SN curves are still used in the design of ductile materials. Then we have for damage, we have the Miner's rule, wherein different factors influencing the fatigue, like stress level, the stress ratio, frequency, all these are considered. So for metals, it's very well understood, the mechanisms of fracture and under fatigue and the crack growth. But when it comes to concrete, all these laws have been applied to concrete, but because of the presence of the fracture process zone, and the mechanisms of fracture and micro cracking are different from those in the metals, so we cannot apply the laws which are available for ductile materials to concrete. Okay, although like the well-known Paris law is applied, the modifications have been made to the Paris law, damage mechanics principles have been applied through the evolution of damage explained through some internal variables and thermodynamic concepts, statistical models are present. But all these are mostly empirical. They don't consider the physical behavior of the material itself. And now with the availability of very good sensing techniques, such as the acoustic emission technique, and also using them in conjunction with digital imaging, we can really understand the complete mechanisms of fracture taking place in this heterogeneous material concrete. So which I'll be presenting in the next few slides. So fatigue in concrete, basically it's a progressive, localized, permanent damage which takes place due to cyclic loading. And more importantly, there are interactions taking place at different levels, the micro, meso, and macro, because we have the cement paste, which is at a very small micro scale. We have the fine aggregate like sand, at the meso scale, large aggregates. So the interactions are taking place at different scales simultaneously. So the process is quite complex, and an energy approach would be the most ideal to describe that process. So wherein also, like when subjected to fatigue loading, we have micro cracking taking place in the concrete. These micro cracks will coalesce and form a macro crack, due to which a lot of energy gets dissipated. So this energy dissipation can be explained through it's an irreversible process. So irreversible laws of thermodynamics can be applied, and the damage keeps getting accumulated with increasing number of cycles, which lead to a stiffness degradation. So to explain this complete mechanism, we can use the principles of fracture mechanics or damage mechanics. So in this work, we have used both these principles, and we have also interlinked them through energy equivalence, so which I will be presenting. Yeah. Yeah, so to explain the mechanisms of micro cracking, Okay, so firstly, I will present you some of the results of the experimental work which we have carried out. We have used 3-point bend beams under flexure. We have used compact tension and wet splitting specimens, and we have also performed tests under direct tension. So here I would like to acknowledge the huge grant of almost 3.5 crores, which was given by IISc to procure a biaxial fatigue testing machine. And also I would like to acknowledge the contributions made by Dr. Sundar in designing this machine for our requirement. I will be showing some of the results of the direct tension in the next slides. So here, let me explain to you about the 3-point bend specimen. So these are 3 different sizes of beams. Okay, notch beams. There's a notch, the small, medium, and large we call it, and they're geometrically similar, meaning the notch to depth ratio is constant for all the 3, and the span to depth ratio is also constant. Okay, so the large specimen is approximately about 0.8 meters. Less than a meter, okay, 0.8. The medium beam is 0.4 meters and 0.25 is the small specimen. Okay, so the thicknesses are constant at 50 mm. So there is a notch provided. Okay, and then we have used these acoustic emission sensors on the. I will show you the acoustic emission sensors later on, all the instrumentation. So these are the loading details. So initially we have performed monotonics, test under a static test, that is under monotonically increasing crack mouth opening displacement. Okay, to capture the complete softening response. So after performing the monotonic tests, we have carried out fatigue tests. And also I would like to mention that the number of researchers working in the area of fatigue of concrete are very few. I mean, people have worked in fracture, but under fatigue, I mean, because of extensive experiments, basically, which requires testing machines, and also the time taken to perform these tests. Some of these tests have taken almost 7 days continuously, you know, for failure. So depending on the frequency of loading. So the number of people doing experimental work under fatigue is very few. Okay, so these are the loading details. This is the constant amplitude loading, and then we have the variable amplitude loading. So in the constant amplitude loading, we have used frequencies. What I'll be presenting is the test performed with the frequency of 2 Hertz. We have carried out with different frequencies too. And the stress ratio, that is the ratio of Pmax to Pmin, is about Pmin to Pmax is 0.1. And in the fatigue test, the minimum load is kept at a small value, about 0.2 kilonewton. This is to avoid separation of the loading device from the specimen, so that there is always a contact maintained.
Sorry to interrupt you.
Yes.
Sir, actually, the slides are not getting changed for everyone. I don't know why.
Okay.
Even some people have written.
Okay, so
slides
what
are not changing.
Maybe I will change. I'm using.
It could be a network
we are
problem.
in the first.
I think you are in slide number 12.
In my
right now I'm in 12.
My page, yeah, in my laptop also it is in first screen only. That is your title screen.
Oh my God.
Oh, Bharati, try to reconnect. It could be the network. It could be the connectivity. Because I'm also seeing the 12
everything
slide
else is recording.
Okay.
Because I have done the recording also. So that is going on.
Okay.
But only the slide, I think.
Maybe I'll switch off my camera also and let me. So I think for those of whom slide is not changing, maybe you can reconnect and and check.
That's a good idea. I see a lot of messages coming in the chat box that they are seeing the 12th slide.
Sync to presenter. How do I do that? You can sync to presenter. I don't know. Translate slides. That's it. Yeah, I don't see it. There is an option to the presenter where the bar of changing the slides is appearing. Yes, there is a bar of changing slides.
Okay.
Oh, the guest is able to change.
Actually,
Oh,
we
one of the
can change
participants is
the
actually
next
able to
slides.
change slides.
Yes. But anyway, that doesn't matter.
This must be a very powerful software.
Or shall I actually, even I'm having slight problem because the screen, although I have a large monitor, but it's not clear to me myself when I'm presenting. Shall I?
No, I think you should now the participants have figured out how to sync with your talk. So just
Oh, they're able to do it?
the way you have. Yeah, I think you're doing fine.
Yeah.
Okay, fine. Then I'll continue. Let us. Okay. Yeah. So in the fatigue loading, the maximum load, we have used it as a parameter where we have changed it to 0.7, 0.8 and 0.9 of the maximum load which was obtained in a monotonic test, okay, in a static test. So in the static test, we had, for example, for a small specimen, we had a peak load going up to 2.8 kilonewton. So in the fatigue load, we have limited the P maximum value of the load to 70%, 80 and 90%. So we have carried out tests under 3 different stress ratios. So for all sizes of the beams. So this is the setup of acoustic emission. So these acoustic emission are piezoelectric sensors operating in the frequency of 35 to 100 kilohertz. We have used 8 sensors and some tests 6 sensors. So 4 in the front and 4 behind. These sensors are connected through preamplifiers and to a data acquisition system. So this is a typical signal which we receive from acoustic emission sensor, showing the duration and the amplitude. And we set up what is known as a threshold of about 35 decibels, because anything below that, especially for concrete, threshold of 35 to 39 works well. So we have set it up to 35 decibels. So anything below that, the signal we don't analyze. And all the peaks which have crossed the threshold, we call that as an acoustic emission count. And if the same peaks are registered by all the sensors or at least 4 of the sensors, we call that as an event. Now here an event can be physically understood as some kind of a micro crack which takes place in the material. So whenever small micro crack occurs, that will result in an event. So in acoustic emission parlance, I mean, an event can be considered as a micro crack. Okay. For digital imaging, we have used a spray paint, a black spray paint on the surface of the concrete beam to get a speckle pattern, and using a 12 megapixel resolution camera, I mean, mounted on a tripod with a remote, we have taken continuous digital images, or we can even take a video, and then later using a good correlation algorithm, we can analyze these pictures and determine the displacements and the strains basically on the surface of the material. So here the idea was to get all the surface information using digital imaging and all the information from within the material, the micro cracks, especially the events which we call it as micro cracks. The complete 3-dimensional location of the event can be captured, okay, because we are using 6 or 8 sensors. So through a triangulation scheme, we can easily get the location of the event where the micro crack is occurring inside the beam. This is the typical setup on a servo-controlled machine. Okay, so to measure the monotonic static tests were performed under crack mouth opening displacement control, CMOD control of about 0.001 mm per second. That was the rate at which the loading was done. And then we have a LVDT to measure the vertical displacements. Here, these are the acoustic emission sensors. They are protected because after once the beam fails, we didn't want to damage them, so they are protected. You can see in the slide. Okay, let me present some of the results. Now here, see this first figure here. I hope you can see the cursor, right? Yeah, I hope you can see this cursor. So in this, yeah, fine. Thank you, Mr. Jadhav. We see the typical load CMOD response. Now the test was performed under CMOD control, and these are the plots, load CMOD plots for small, medium and large size beams. Okay, so what we see is we see an initial linear response, and then after just before the peak load, we can see a non-linear a region which is deviating from the linearity, and then it reaches the peak load. After the peak, we see the typical softening response for all the beams. This is for the monotonic load. Under fatigue, what we see is that this was performed under load control. Okay, so these are the results for a 2 Hz frequency. So what we see is this is the load versus CMOD response, and we see that with increasing number of cycles of loading, there is a gradual decrease in the slope of this load CMOD curve. Okay, the slope gives us the stiffness. So which means that there is a degradation in the stiffness gradually, a gradual degradation taking place. Now, for each of the small, medium and large beams, here we have this the static response, which is shown by the dark black curve, and the fatigue response on the same size specimen is shown inside by red. Okay, so what we see here is under fatigue loading, the final failure occurs, with a very small CMOD at failure, okay, compared to the CMOD in a monotonic static case. So here you see approximately about 1 mm is the total at failure, 0.8 to 1 mm in a static test, but the CMOD at failure in a fatigue is much, much smaller. And what we see is in most of these cases, the static curve serves as an envelope. It envelopes this fatigue response. And because of this, people have used the static envelope curve criterion to determine the failure due to fatigue. Okay, but we did test on many specimens. We saw in some cases, even some of the under the fatigue loading, it has crossed the static curve in some cases. So, so one question arises: can this static curve be used as a envelope to determine fatigue failure? So, which we will answer that in the coming slides. There is some problem in this. The curve is missing. This is missing. There is a load CMOD curve which I don't see. Do you see in your screens a black line showing the load CMOD curve? No,
the black line is not seen.
Not seen. I don't know why that is not seen. Okay, basically then I'll skip this. Okay. Okay, what you can assume is like there is a black line which you just look at my cursor. So it goes up to the maximum peak here, and then you see the softening response coming down. Sorry. Coming down, and we have able to, using digital imaging, we have computed the crack length. This is at the peak load, there is no, we don't see any crack. This is at 50% in the pre-peak region, no crack, but at the peak load we see a small crack which has occurred, and then in the post-peak response we see the major cracking taking place. And this is at final failure where we see the tortuous crack which has occurred, and that has led to the failure of the beam. Okay, here we see the degradation in the stiffness. So these we have plotted the load CMOD response in a fatigue experiment, obtained from the fatigue experiment at say like a few cycles, so that we can compute the slope of these. And the slope of each of these at different cycles are plotted here, which gives us the stiffness. So we have plotted the stiffness on the vertical axis and the cycle ratio here normalized with respect to final failure. And what we see is for all the beams like small, medium, large size at different stress levels, 0.7, 0.8 and 0.9, we see that the behavior is very similar. The degradation in the stiffness, we see the slopes are all the same, for different stress levels and for different size of specimen. So what it means is we can use this rate of degradation as a material property, in order to develop fatigue laws. Okay. And then in this table, what you see is the crack mouth opening displacement in millimeters. This is for small, medium, and large beams. Okay. The first row here, monotonic at peak. So what we see is at the peak load. Okay, at the peak load in a monotonic test, these are the crack mouth opening displacements. At failure, the crack, as I told you earlier, at failure in a monotonic test, the crack mouth opening displacements are quite large. Okay. Now, in a fatigue test at 70%, 80 and 90% of the stress ratio, so we see that these are the displacements, and these crack mouth opening displacements are in the range of the monotonic at peak. You see these values. So all these values are in the similar range as that which takes place in a monotonic test at the peak. So again, this can be used as a failure criteria under fatigue. That is the crack mouth opening displacement at the peak load in a monotonic test, which could be used as a failure criteria. Now here in this, we had this, this is a softening curve which was missing in the last. So here I have both the digital images and also the acoustic emission results. So these dots in the acoustic emission, these are events, and we have different size of these dots. The blue are different size or different colors. The red one is the largest. Okay, the size. So these are classified based on the energy of a AE event. So if a micro crack appears inside the specimen, so these are all the micro cracks which are appearing inside the specimen, which are projected on the surface. Okay, so what we see here is on the surface, we have projected all the micro cracks which occurred, and the smaller dots, that is the blue, light blue ones, they are the events or the micro cracks with low energy. So we have classified into 4 energies. The smallest is the blue one, and the red one corresponds to the high energy event. So what it means is the micro cracks which occur inside the specimen, when they coalesce, when they join and they become a larger crack, so the energy content in them will be much higher. So as these larger cracks develop into much larger cracks or a major crack, then we have a high energy which is dissipated or which is released, and those are captured by these red large size markers here. Okay, so now with this understanding, let us look at the behavior. So at the peak load, so this is 0 to B. So at the peak load, we have the AE events. 37 AE acoustic emission events have occurred. So that is less than 1% of the total. The total at failure were about 6,258 events or micro cracks, and only less than 1% have occurred when the peak load has reached. And also what we see is, it is the 20th slide which is going on. There was a question. So, and what we see here is the red marker, we see the red dot, that's the high energy events along with the blue markers, in this 37 events. So there's a combination, simultaneously all energy events are occurring. Now at the point C, that is in the post-peak response, okay, that is approximately 50% of the load has come down. We have seen on the surface through digital image, we have seen the major crack, and also we see about 2.5% of the events which have formed. And continuing, so at point D, so we see that nearly 37% of the events have been formed, and at E, where final failure occurs, 6,258 events have occurred. So what it means is that the number of events, so after the peak is reached, micro cracking takes place, and all these micro cracks, here we see that there are different size markers which are shown for the events. So high energy events are increasing. That means a micro crack is coalescing and forming a macro crack, and final failure takes place due to the propagation of the macro crack, which is also seen in the digital image picture on the surface. Next, under fatigue, we see a different kind of mechanism. See here, what we see is we are plotting the maximum CMOD on the vertical axis and the normalized fatigue life. Okay, the fatigue life is normalized with the final failure value. So 0 to 0.25 indicates 25% of the fatigue life. Okay, and so in the first 25% of the fatigue life, what we see is only 2% of micro cracks or events have formed. Okay, 2% of the final 3,347. So in the next 25%, that is up to the 50% of the fatigue life, only 4% of micro cracks have formed. Now, the reason for this is, see, the amplitude of loading is smaller. I mean, we have not gone up to the peak. It's about 80% in this figure, 80% of the peak. But, although 50% of the life has passed, still the number of micro cracks which are formed is very much lower. And what we see here is only the small dots, that is the small the events of low energy. But in the next, that is from 50% to 75% of the life, we see the acoustic emission events increasing. So it has gone up to 20%. But what we see in the final 25% of its life, 80% of the micro cracks have formed. Okay, and this image showing the crack profile on the surface, we see there's hardly any crack which propagation, and this is taken one cycle prior to failure, and this is at failure. So what we see here is just before failure, all these micro cracks, they coalesce and form a major crack, which are shown by these yellow dots here. Okay, the higher energy events. So in the case of fatigue, the final failure takes place suddenly. Okay, so the number of micro cracks which are forming are they are localized, they are very few in number, but after about 75% of the life, all these micro cracks, the rate at which the micro cracks form is very large, and they coalesce and form a major crack leading to final failure. So that is a difference. Whereas in the case of monotonic static loading, we see that high energy events are formed right at the beginning, and which is seen in the next slide. So here in this, we see what we are plotting here is the AE energy in autojoules. Okay, this is a normalized time. It can be normalized CMOD as well, because it was done under CMOD control with a constant rate. And this is the load on this axis. So the black line indicates the load versus time relationship, or load versus CMOD relationship. And these dots, these blue ones, are the low energy meaning energy level from say 0 to 10 power of 3, 1000 autojoules. So these are the low energy events, followed by the green, the orange, and the red. So red ones are the high energy events. So in the case of a monotonic static test, we see that right from beginning, we see all energy levels are present in the events, and there is a simultaneous interaction, especially during the softening region. We see the growth of micro cracks to be very large, and at final failure, this reduces. Okay. Whereas in the case of fatigue test, this is under fatigue, we see that almost up to 75% of the life, not many micro cracks are formed, and we don't see these red dots in the initial during the initial life. It's because a lot of only small cracks are formed. They are dispersed across the depth of the specimen, and only during final fracture we see this red dots indicating that all these minor cracks, they coalesce to form a major crack, and sudden crack propagation takes place. Now here we see in this curve, we plot normalized load and A by D. That is a crack length which we obtain from digital imaging. So this line, this black line here, with circles, that indicates the growth of crack, which we have seen normalized with respect to the depth which you have seen from the digital images. And each of these lines indicate the energy, the growth of these events, with time. So here we see energy level E1, E2, E3, and E4. And the final purple line is the total energy, cumulative acoustic emission energy. So what we see is when the load has reached about 20%, or 40% or 60%, all the energy events, there is a surge in the events. Sorry. There is a surge in the acoustic emission events of all energy levels. Okay, now why does this happen? It's because of we have a notched beam, and initially because of stress concentration and also some kind of a redistribution in the stress taking place at the notch tip. So micro cracks are formed. Micro cracks even coalesce and form a larger cracks right in the beginning. But then with increasing crack mouth opening displacements, so we see there's a gradual increase in the low energy and the higher energy events, and later on becomes more or less constant. Whereas we see an opposite trend during fatigue loading. So in the fatigue loading, the energy levels E3 and E4, which are shown, occurs only after 70 or 80% of the fatigue life. We don't see them occurring in the beginning. Whereas energy levels E1 and E2 we see occurring at the beginning, and also the crack growth. See, initially up to 50% of the fatigue life, it's horizontal, meaning there is no crack growth. We don't see any crack in the digital images, but after 50% of the life, we see that there is an increase in the crack growth on the surface, and then finally we see this becomes vertical, meaning a sudden crack growth takes place, leading to failure. So from acoustic emission and digital imaging, these two techniques complement each other, and we are able to obtain the complete mechanisms of crack growth, their coalescence, and formation of a macro crack. Here we see again the difference through these bar charts, wherein these indicate the percentage of the blue ones are the events, that is the microcracks, and the orange one is the energy. So what we see in under monotonic loading is nearly 70% of the events are formed initially, but the energy is very low. That means at the beginning, a lot of microcracking does take place, but the magnitude of energy release is low. But at final failure, the higher energy acoustic emission events are generated, leading to the final failure. Whereas in the case of fatigue loading, almost all different energy contributions are there. I mean, and the number of events, you can see that the E1 corresponds to the large number of events, almost 90% of the events compared to the energy level 4. That means only micro cracks are formed for almost 90% of the life, and later on, just before failure, they coalesce and form a macro crack. So it's more what we can say about the failure is it's more like a brittle kind of failure, a sudden failure which occurs under fatigue loading. Yeah. Now from the acoustic emission events, we can see we can also plot the density curves, the relative density of the localized events, and we get a picture of the shape of the fracture process zone. The morphology of the fracture process zone can also be obtained from the acoustic emission events. Here, the size of the fracture process zone is calculated, okay, using the distribution of the acoustic emission events. So we draw a histogram. This is the front face, that is the beam length, what we are plotting this on, and this is the depth of the beam. So here we are drawing a histogram. You can see a black line here. Sorry, click there. A black line appearing here. So the intersection of this histogram with about 20% of the total acoustic emission events will give us the depth of the fracture process zone. So same thing here, we have the histogram here, and about 20% of the intersection of this 20% line with basically this 20% line was arrived by other researchers, which is available in the literature, and they had proposed this 20% line through which we can determine the width of the fracture process zone. And here we can see the thickness. Along the thickness also what we see is all different energy acoustic emissions are spread across. So that means across the thickness we see all energy events, but due to the free surfaces on these two sides, we see more large energy events occurring in the middle portion. So we could obtain the complete size of the fracture process zone for the case of monotonic loading, which we have, which is shown in this table. But for fatigue loading, we don't see this. We see only a very localized, narrow zone of only low energy acoustic emission events. So we can't really predict, we can't use this method to compute the size of the fracture process zone. So what it means is like, is there really a fracture process zone under fatigue loading? So that is a question which we had. I mean, see, under monotonic loading, we could see the development of the fracture process zone. We have computed the width, the length, and the depth. And also another interesting thing is like the ligament, we have the ligament length. So when we normalize the size of this, the length, the width, and the thickness of the fracture process zone with the depth of the specimen, we see that we get a constant value of almost 0.78 or 79, 0.79. For all different concrete mixes, for different sizes, okay, for different size and different concrete mixes, we see a constant value of the size of the fracture process zone normalized with the depth. So what it means is we can use this as some kind of a material property. We can use this as some kind of a characteristic length, which is used in most of the nonlinear models. Okay, but now coming to the fatigue loading, we don't see a large fracture process zone. So let's look at other results. Now, generally the fatigue failure criterion, to predict the fatigue failure, the static envelope curve is used. The static envelope curve states that the monotonic or quasi-static response of the specimen, which is shown here by the dotted line, this is the quasi-static response. So this response serves as a bound for either the displacement or the strain values for a specimen subjected to fatigue loading. So this implies that the failure strain, this is the failure displacement or the failure strain can be obtained, okay, between this max, sigma max and this minimum. So when the sigma max hits the static curve, so this is considered as a failure criteria under fatigue. Now what we have seen is in some of the specimens, this fatigue, I mean the data from the fatigue, they are not bounded within the static curve. This is a static curve and it is not bound. It has crossed the fatigue. So if we use this as a failure criteria, we have to use the point C. At this point C, wherein the fatigue response hits the static curve, this CMOD corresponds to the failure criteria, failure value. But what we see is at the peak load, at the peak load, this corresponds to the inflection. There is an inflection point here in the normalized cycle to the CMOD curve. So this peak value hits the inflection point. Okay. However, if you look at the failure value D, this is where failure takes place in fatigue, the CMOD, we get another value of CMOD from the static response. So what it tells us is this kind of static envelope curve, I mean, this may not be suitable. It is not suitable, especially for a material like concrete. The best alternative would be to use the CMOD at the peak load where there is a clear inflection point to establish the failure criterion for fatigue. And also the mechanisms we see here. See, this is for monotonic case and these two are for the fatigue case. So in the monotonic case at points B and D, I'm showing you the events which are occurring. So we see that high energy events have occurred in a monotonic test, but whereas in the fatigue case, we have only the low energy events and hardly any. So that means these are just the micro cracks. They are not even coalesced to form a major crack. So using the static failure envelope criteria is erroneous and is not suitable for concrete. That is what it tells us. Now I'll show you some of the experiments from direct tension. So this is our biaxial fatigue testing machine. You can see the size of this machine with respect to this wall. I mean, this is the roof level and this is the first floor level. So this is the size, I mean, of the machine. We have 4 actuators, okay, which can be independently controlled, and we have a specimen which is loaded here. The specimen is a concrete specimen with 2 notches, okay, and performing a direct tension test on concrete is really difficult. because gripping the specimen at the grips, the failure takes place and we will not get a complete softening response. So in this case, what we have done is like we have put a steel plate, which have matching threaded holes matching with the holes in the on the machine, so this is done at the time of casting itself, and after the specimen is cured for 28 days, the specimen is fixed through bolts. So there is a bolting arrangement to fix the actuator to the specimen. And let me show you some results. So this is the typical, again, softening response. Again, we are performing this direct tension test, and after the direct tension test, we'll be doing fatigue test in direct tension, in compression, and a combination of tension and compression. This is basically to get a complete failure envelope for concrete. The current day in all the finite element models, the failure envelope or the failure criteria which is used are based on experiments which are done on very small specimens, lab size specimens, which are basically cubes of 150 millimeter cube, so very small specimen. And these failure criteria are applied to structures like dams and bridges, which are very large. So, and since concrete exhibits a strong size effect, I think we have to make a correction for those failure criteria. So the best way is to perform these tests on large specimens. So here large, when I say as large as 1 meter by 1 meter, okay, instead of using 150 millimeter cube. So that is what we are planning to do. But these are the preliminary results. What we see from the acoustic emission, we can see under direct tension how the evolution of micro cracks has taken place. We are still working on this. And what we see is the number of events. So again, here in direct tension, we see that all events of all energy levels are formed. Okay, basically it is happening after the peak load. Okay, in the case of direct tension, and the way failure takes place, is shown by this curve. Okay, normalized acoustic emission events and the crack length. So both are plotted here. The crack length is obtained from digital imaging. The acoustic emission events are micro cracking through acoustic emission, and this is a normalized CMOD. So we can identify 4 distinct regions. First region where there's no cracking, no crack propagation, we call it as stage 1, the elastic stage. Okay, the linear elastic stage. The second stage is the micro crack initiation stage. So you can see a lot of micro cracking which has occurred here. Sorry. And then the third stage is the steady crack growth stage. So we have a steady, so we can see the rate of crack growth on the surface as well as from the rate at which the micro cracks grow. The slopes are almost similar. And then the final stage where major crack grows and leads to failure. So these could be clearly identified from this experiment. Okay, those are about the experimental results. So let me next go to the now, how do we make use of this experimental results in developing a fatigue crack propagation law? So people have used the Paris law, the modified version of it, and they have obtained many empirical relationships. But what we thought is we have now a good set of experimental data. So why not use, because we see that the energy dissipation takes place. Thermodynamics is the best subject to apply, for fatigue crack propagation through what is known as the dissipation potential and entropy. So here, starting with the simple basics of thermodynamics, wherein we have a thermodynamic system which are completely determined through state variables. So in the state variables, we have these observable variables like strain. We can observe it. We can fix a strain gauge. We can fix a thermocouple, get the temperature. And then we have other variables known as the internal variables. So which can be elastic strain, inelastic strain, or area of a crack, which we have made use of in this analysis. And then then we have the thermodynamic properties. So associated with these state variable, we have the associated variables. So the associated variable connected with strain is the stress, with temperature is the entropy, and so on. So we define 2 potentials, thermodynamic potential and dissipation potential. This thermodynamic potential describes the elastic behavior. That is the through which all the laws of linear elasticity can be obtained. Whereas the dissipation potential, this thermodynamic potential is a relationship between observable and the associated variables. Whereas on the other hand, we have the dissipation potential, which is a relationship between the internal and the associated variables. So this is due to the some kind of dissipation taking place, like it can be due to friction, it can be due to collisions, it can be due to cracking, micro cracking, and so on. So in our work, micro cracking takes place wherein a lot of energy is dissipated. So we can relate all these through a dissipation potential, and for second law of thermodynamics to be applicable, this potential should be continuous, convex, scalar. So there are certain laws which have to be satisfied. Okay, then so in this the best way to define the dissipative forces is to assume that there is a potential which exists, okay, which is sub-differentiable function of the internal flux, meaning we have a potential here. This phi is a potential. So we want to establish a relationship between the internal variable and the, so as we see here, by the associated variable and the internal variable. So here to start with, we have done using fracture mechanics and damage mechanics. So for fracture mechanics, we have used the area of the crack or the length of the crack. We can assume because the thickness is constant as the thermodynamic force, and the crack is propagating due to the energy released. Okay, this is some kind of a force which we are applying. So we have developed a relay. So what we need is to get the rate at which the crack grows, A dot. Here we need a potential. Okay, a potential function is required, and this potential function is available in the literature. They are from some empirical relationships are present, but here we thought we will make use of dimensional analysis to obtain the relationship of this potential from first principles using all the factors which contribute to it. That is the force parameters, loading parameters, which are contained in this delta G, that is energy release, and the R, the resistance. Then we have the geometry properties, that is the area of the crack. Then we have the material properties parameters, the fracture energy, or the fracture toughness, and the tensile strength. So we have included all these factors to and using that. So these are the different variables which we have used, and these are the dimensions of them. So through dimensional analysis, we could obtain a expression of this type for the potential. So from this potential, we can obtain the rate of crack propagation. Okay. Now there are two constants here which are determined through calibration of some experimental results, which we have done here and obtained this. Yeah. So this is a calibration. We see that, we have calibrated this from the experiments here, from experiments of Taumi et al. And others, Taumi and others, whereas we have validated using the experiments of Bazant and then other experimental results which are available, and we see that we get a very good agreement between the model which we have obtained. So this is another validation using different experimental results for different R values. Again, we see a very good agreement in this. And we did a sensitivity study wherein all these parameters, different parameters which are involved in this rate of crack propagation. So those are considered as the variable, and through the mean and standard deviation, we obtain the tornado diagram and find that the crack length is the very sensitive parameter. So in order to determine the crack length or the number of cycles to failure, the crack length, have to be resolved at a very smallest level. Accurately, we have to obtain that. Simi, that is from fracture mechanics. Same thing we can apply. I'll skip some slides in the interest of time. I'll take about 5 to 7 minutes now. So again, instead of taking the state variable earlier, we took the crack area, we take a damage zone, some kind of not damage, a damage parameter. And then we have an associated variable, which is the damage strain energy release rate. Again, through dimensional analysis, we could obtain the dissipation potential from damage mechanics. So this is a potential from damage mechanics, DM. And using dimensional analysis, we could obtain a relationship between the rate of damage and other physical parameters, including the material parameters, the loading parameters, and also the geometry parameters. And the damage which we have considered, so it's a scalar damage wherein 0 stands for no damage or no cracking or no reduction in stiffness, whereas D equal to 1 stands for fully damaged. So here we do like, we consider a representative volume element and we propagate the crack step by step. And we can determine the number of cycles taken for the crack to propagate in each step. That is, when in each step we assume that the damage initially is 0, and once it reaches 1, we determine the number of cycles and we carry out the analysis. So these are some of the validation, and we see that the experimentally obtained failure cycles are in close agreement with the what we obtained from the model. Let's get that. Now, since we have obtained both the dissipation energies, dissipation potentials from fracture mechanics and damage mechanics, we have tried to connect both these through the principle of energy equivalence. So in the energy equivalence, so we have a damage zone, and in the fracture mechanics, we have a crack. So the amount of energy required to propagate the crack should be same as the amount of energy dissipated in a certain volume of the damage zone. So using this kind of energy equivalence, okay, between the two systems. So here we have a crack and here we have a damage zone. So using both the thermodynamic potentials from fracture mechanics and damage mechanics, we could move from one theory to the other. That means if we have, especially in any finite element software, if we have a software which uses the discrete crack models, okay, and we know the damage zone, so we can convert it into a discrete crack. Or alternatively, we have a software which can which uses continuum damage mechanics, and we want to convert it back to a discrete crack. We can use this energy equivalence. So it will help us in moving from one theory to the other. That's the advantage of this. So that's the, I just did this. And most importantly, we see that the acoustic emission events which are generated, so this is the front view, top view, and side view of a small beam. And we see that in the front view, we have seen these events which are taken place. Top view is across the thickness. What we see is the whole thickness, and the side view is when we take a section here, when we take a section across this. So for small, medium, and large size specimens, we have the acoustic emission events. We have computed the size of the fracture process zone. So we know the damage zone, and through using the energy equivalence, we could obtain a very close match between what we have obtained from acoustic emission and through energy equivalence. The last part is about the entropy. See here, basically according to the second law of thermodynamics, every irreversible process meaning that means if we reverse if we load a specimen and a lot of frictional energy dissipation occurs or due to micro cracking, on reversing the load, we cannot recover this, okay, the energy. So it's an irreversible process. So this is accompanied by a gain in entropy, okay, and the amount of entropy gain depends upon the degree of irreversibility. So the energy dissipation which can be related to the entropy gain through this relationship where T is the temperature here, S is the entropy, rate of entropy, and E is the energy dissipation rate. Okay, so now the thermodynamic system which we have considered is the 3-point bend beam with the fracture process zone with a crack. Okay, so this is a thermodynamic system. So here again, once again, using dimensional analysis again, okay, starting from first principles, using all the variables which contribute to the rate of gain of energy or the entropy, we could establish a law, okay, for the energy dissipated. And then again, the calibration and validation is done with experimental results. And here we see what we see is, this is on the vertical axis, we have total energy dissipated versus the number of load cycles. That means for a given load cycle, the amount of energy dissipated is the same for small, medium, and large size specimen, what we see here. That means this is this energy which is dissipated does not depend on the size of the specimen, and it also here for the again we see the same behavior for a different concrete mix. So and the entropy at final failure we have plotted here, and this for any size, the depth of the specimen is plotted on the horizontal axis. This we see almost remains constant. Again, this final fatigue failure entropy can be used as a material parameter, or it can be used as a failure criteria to determine the number of cycles which takes to dissipate this amount of energy. So it can be used as a failure criteria. So in conclusion, so we have seen by using the acoustic emission and digital image data, the process of microcrack initiation, coalescence to macrocrack, and the stable crack growth could be very well understood in a quasi-brittle material, and the different failure mechanisms under monotonic and fatigue loading are understood. So what causes the failure under monotonic and under fatigue, and fatigue crack propagation laws are proposed from first principles using dimensional analysis in conjunction with thermodynamics laws and the concepts of fracture and damage mechanics. And the future directions, we all know that concrete structures such as highway pavements, bridge decks, airport runways, railway sleepers, machine, all these, they are subjected to fatigue loading, cyclic loading. So wherein progressive damage takes place. Now we have seen that, established that through the acoustic emission that the damage process is progressive. It's takes place very slowly, but a final failure occurs due to the formation release of large amount of energy. So what is required is we have to quantify damage. First, you have to define damage, then quantify damage in structures which are under service, use the damage evolution law and predict the remaining life of the structure. So this is what is required, which we are working on. Thank you.
So thank you, Professor Chandra Kishen, for an exciting talk. So let's kind of give a round of applause from the audience. So I'm sure there are some questions from the audience. So if there is anything, can you just put it up in the chat box? We will go through that. Bharti, we expect them to type in the chat box, right?
Sir, one question has come. You can see that.
Okay, Mahendra. He is, said that thank you for sharing your knowledge. Simal Basaran is using unified mechanics theory for metals under fatigue. Is the entropy model you presented related to that? That's one question.
Yes. We are following his work, Basaran's work, especially in the thermodynamic modeling, and the mechanisms what you see in ductile materials. He's working on steel, the ductile materials. The mechanisms of fatigue is different in case of quasi-brittle materials. So having understood that the mechanisms are different, and also the way the energies, different energies contribute to different type of microcracks or coalescence into macro cracks. So this entropy, the theory of entropy could explain these mechanisms very well.
Okay. So there is one more question from Bineet Kumar. What are the reasons for size effect in concrete?
Yeah, as I showed you in my first slides, the size effect, it's basically, see, there are different theories. One is the statistical size effect, which explains, see, one theory is as the size of the structure increases, the probability of having defects or more number of defects, the probability increases. So due to which large size, the nominal strength of large size structures come down. Okay. So this is one theory which explains. Another theory is based on the Weibel's weakest link theory. So again, these also, they are correlated. So large size structures. So the size of the fracture process zone is very small when compared to the crack length. So that is the reason why we see the decrease in the nominal strength and the size effect.
Well, I mean, I might just interject and ask this question. See, for the case of metals, when we are talking about the size scale effect, especially when we deal with the small size specimens, we normally say that the minimum size is characterized by the grains,
The
the
grain
size
size.
of the grains. Yeah, right. So we say that at least 5 to 10 grains should be participating in this process. So is there any equivalent that is there with
Yes,
reference
there is
to?
a equivalence. I mean, based on there is so initially to describe these effects. I mean, the fictitious crack model by Hillerberg was used, and later Bazan came with his crack band model. So in the crack band model, I mean, the size of the crack band, was fixed as some kind of between 3 to 5 times the size of the maximum aggregate used in the concrete mix. So there is a very similar correlation between the two.
Okay, there is a question from Sundar. Considering the effect of water and moisture on strengthening the concrete, is there any observable effect of lab conditions and humidity on long duration fatigue crack growth?
No, actually not, because the process of hydration. See, when we prepare concrete, we assume that there are no water molecules present in the concrete. I mean, we assume that the complete hydration has taken place, because especially in concrete, when we add water to cement, there's a process of hydration. So a formation of a calcium silicate hydrate, which leads to the strength growth. I mean, so that forms, and it takes about 28 days for a complete hydration. So once the concrete is, the cement is completely hydrated, then we assume that there are no water molecules.
There is one
So
more
with
question.
age, I think there'll be no change in the fatigue behavior.
Okay, but just again to interject, does the setting time of the concrete and the grade of the cement, does it kind of affect the response during fatigue? Like today we talk in terms of 53
Yes.
grade and so many things, cements. Yeah.
Well, yes, it's the grade does not really matter. It is the strength of the concrete finally. That is the cement content, and together with it, the ingredients, the water cement ratio. So all that plays a role in determining the strength of the concrete. So the strength of the concrete, basically it's the compressive strength of the concrete mix, and the tensile strength of the concrete is related to the compressive strength. So instead of the grade, we can say it's the grade of concrete or the compressive strength of the concrete which matters.
Oh, okay, good. So the next question is from Shubham Sharma. Is the size of the process zone a characteristic property of the material, or is it dependent on the size of the specimen?
No, that is what I had shown, that from acoustic emission through the statistical analysis, we have determined the size of the fracture process zone. I think this is one of the first attempts to determine the size of the fracture process zone. And the normalized value with the depth, we see that we get a constant value. So for different mixes for different sizes, so across we have got to obtain a constant value. So we can use that as a characteristic length or the size of the for concrete.
So there is one more question from Mahendra. Can we summarize from your experiments the following? A, for monotonic loading, localized cracking is present. B, for fatigue loading, a more distributed damage occurs.
No, it's the other way. For fatigue, it's more localized. There's no formation of a fracture process zone. Whereas under monotonic, we have a larger size of a fracture process zone. We have the cracking takes place in a much larger area. In the case of a monotonic, large number of events are formed or the micro cracks form. These are distributed in a zone. But the ones which we see along us, there is another definition. Within the fracture process zone, there is what is known as a fracture core zone under monotonic loading. So the fracture core zone is where we have those, if you remember those red dots, I mean, it's more localized, wherein the macro crack forms. So what I understood from a question is, in the case of fatigue, you say you would ask me whether there is a large
More-
size. No, it's very localized in fatigue, under fatigue.
Okay, so A and B has to be just
Reverse.
interchange for the.
Interchange.
Are there any other questions from the audience? Anybody's typed in the questions? While they are doing it, Professor Chandrakishan, I just wanted to ask, see, normally if you look at acoustic emission, I'm happy to see that, you have used multi-sensor methods to, characterize the fracture process, which is one of the tools that I am also using, but with reference to metals and composites and things like that. Did you try using, say, thermal imaging? You have done the digital imaging, right?
No, I have not, but recently I have procured a thermal infrared
Oh,
camera.
okay.
I want to try it out. Yes, I have just procured one. Yeah.
What does the literature say? I mean, like, does it kind of help
No,
in
thermal imaging, especially what the literature says is we can determine some kind of a, see in concrete, actually it will be very difficult because the change in temperature is not very large to be captured by an infrared camera. However, I'm trying it out. But yeah, the literature says it's, especially when you perform a fatigue test, the heat generated is not sufficient to be captured. I mean, for the, or maybe I should use a very high sophisticated infrared camera.
Yeah, what is the NETD of your camera that you have got? Is it 0.05 Kelvin?
No, it's a, I don't remember the specs, but it's a low value, it's at a lower end of the higher end camera, yes.
Okay. Then the other question is, see, normally for metals, we use acoustic emission to identify the crack initiation. Okay, but from your slides, what I can see is that, at Pmax that you didn't have so much amount of acoustic emission activity, but during the unloading segment, as the crack length is increasing, your acoustic emission activities were showing up high.
Yes.
So is that a kind of, usage perspective, it's different between metals and composite, concrete?
Yes, I think that is a physical difference, basic difference, which metals and quasi-brittle materials.
Okay.
See, basically what happens is we see the material is not perfectly brittle, meaning at the point where we have a notch, there's a sudden stress concentration and sudden failure takes place. It doesn't happen. And also we see at the peak load, the material initially before the peak load itself at about 80 to 90% of the peak load, we see a deviation from the linearity, which means small micro cracks have formed, which is because of which we see the deviation from the linearity. But after the peak load is reached, the micro cracks are forming in front ahead of the notch, and it blunts the notch. It blunts the notch, and then it's unable to sustain that maximum load. So more and more, so as some kind of unloading takes place, redistribution takes place, more and more micro cracks are formed, and we see a reduction in the load carrying capacity.
Is that related to the rate of loading? Because, if there is a delayed recovery at the fracture process zone, you could end up seeing different kind of acoustic emission activity.
There is, rate of loading also plays a role. But here, when we perform a monotonic test, static test, basically, we want to study the way the microcracks are formed in the fracture process zone. So we use a low rate of loading. But concrete shows strong
rate dependency.
Rate dependency, yes. It does show, yes.
Okay, and before I kind of go to the next question from Mahendra, I'll just ask this question. In metals, normally we correlate the DC by Dn, or D absolute energy by Dn, as a function of the crack growth rate. So is there a similar approach that one can think of for this case of concrete from the acoustic emission data?
Yeah, we have tried out the acoustic energy, relating the acoustic energy to the fracture energy, which
Okay.
the energy required for crack propagation.
Mhm.
We could establish, but we are not. I mean, with more and more experiments have
Okay.
to be performed with different parameters so that we can really confirm this.
Yeah, normally what they say is for metals, if dA by dN, that power law exponent is some number, you will find that the acoustic emission, when you try to get this as d energy by dN versus
Yes.
delta K, if you plot it, it will be normally like the M or N plus 2 or some numbers.
Right, right.
So, yeah.
Actually, we have one of my students has done that. I mean,
Okay, okay.
we have obtained, but I have not presented in that
Oh,
in this presentation. But we have to again, I mean, do more tests to confirm this.
good. I think last question from for fatigue loading, the region of microcracks where energy dissipation occurs is spread throughout the entire specimen just before failure, and hence a more localized crack forms. Is this okay to say? This is
No, no,
what Mahendra is.
could you please repeat that under fatigue?
For fatigue loading, the region of microcracks where energy dissipation occurs is spread throughout the entire specimen just before failure.
No,
And as a
no. This is not true. It's not spread
okay,
throughout. It's in a very, very localized zone.
okay,
See,
but
when you
he
say
says
spread throughout, let me clarify this. We have the length of the specimen. So along the length, we don't see it's very localized. But along the depth, it's the crack which is the major crack propagates along the depth. Along the thickness, yes, it's distributed across the thickness. So if I cut the specimen into two along the notch, what we see when we see the thickness of the specimen, it is distributed across the thickness. But if I look at the length, overall length of the specimen, the span or the length, it's a very, very small zone over which these micro cracks have spread.
oh, okay, okay. Yeah, so there is one more. Can you suggest some good reference books for fatigue crack growth theories, modeling, and DIC techniques?
DIC techniques, if you go to iMechanica website, you get a freely downloadable DIC algorithm. Maybe you can send an email to me, I can send you that, or you can look at the iMechanica website for DIC. And for fatigue, yeah, there are many books on fatigue, many papers on fatigue. So
Okay, good.
Fatigue
So,
by Suresh, yes, Subra Suresh, I mean, which
yeah.
is not just for concrete, but I mean, it's for the metals basically, but that's a good book.
Yeah. So if there are no more questions, I think we will thank Professor Chandra Kishen for his excellent illuminating lecture that he delivered to the InSIS IITM webinar. And let's all clap our hands in appreciation of his talk.
Yeah,
And
thank you,
before
Professor, for
thank you. It was our pleasure.
recognizing
In
this.
fact, I'm looking forward to listen to your talk on fire-induced damage to concrete structures, because I believe
Yeah, nowadays we see a lot of fire accidents. Every other day we see large fire accidents taking place, and we have quantified the amount of damage, especially in concrete structures, which has occurred due to fire. And more importantly, what we have seen is the reinforcement after fire, after about 2 hours of fire, the yield strength of the reinforcement has come down from 500 MPa to 360 MPa.
Oh,
so
okay,
that is the most dangerous thing which you have seen happening.
Okay. So that means obviously you are looking at repair methods for such
Yes,
fire-related
including
accidents.
repair is not just repair of concrete, but the steel also, I mean, has to be replaced.
Yeah, I think that's interesting because steel would have undergone some microstructural changes.
Yes, changes
because of this sudden heating and cooling response. Yeah, right. So I would imagine that. So hopefully some other day we will listen to you on that aspect. And one more thing that I wanted to see is that are you working in corrosion related problems of concrete?
No, I'm not looking at corrosion.
That's another aging, what you call the civil structures.
Yes,
Concrete
no, there are many.
related.
Almost, I think every IIT, I think professors are working on corrosion indeed.
So thank you very much. And let's kind of give a big round of applause to Professor Chandra Kishen. So
Thank you and not all the participants today. Thank you.
And next month, 23rd, I will have Professor K. Ravichandran from University of Utah, Salt Lake City, who will talk in this webinar. So the details will be shared to the participants through email, as usual, like what Mrs. Bharti is doing. So thank you very much. And Bharti, thank you. And I'm transferring the control to you.
Thank you,
So we
sir.
can sign off. Can we sign off now?
Yeah, I will
Okay.
stop recording.
Yeah.
Thank you, sir.
Please. Thank you very much.